Section 5.5 revolves around solving exponential and logarithmic equations. And here's your typical exponential equation. Now, if you run across one of these, the easiest thing to do is try and find similar bases. What I mean by that is 16 can be written as 2 to the 4th power. And the nice thing about exponential equations is they're one-to-one. So, if I can get a similar base, I can basically throw out the base and just worry about the exponents. So in this case, I can write this equation as something with a similar base. At that point, I can ignore the base and just bring down the exponents, and I'm done. X equals 4. In something that's a little more complicated, we do the same thing. Once I find a similar base, I can ignore the base, bring down the exponents, and then solve. So I'll bring the 3 over, and divide by the coefficient, and we have our answer of 5/4. That's the easiest way. But often you'll run into problems that look like this. And no matter what we do, we can't express either the 5 or the 11 as something with a similar base. So what I'm going to do in this case is use the properties of logarithms to get the variable out of the exponent. So the first thing I'm going to do is take the natural log of both sides. And if you like using common logs better, that works just as well. You get exactly the same answer. And now, using the properties of logarithms, I could bring that x out in front. Like so. Now, I have my variable, a coefficient on my variable, even though it doesn't look like quite the normal form, equals some other number. So all I have to do is divide by the coefficient on my variable. That cancels off, and I get x equals natural log of 11 over natural log of 5. Now if you're asked for an exact answer, this is it. That is the exact answer. If you're asked for an approximate answer, just plug that into your calculator and get your approximate answer. Let's try one that is let's try one that's incredibly simple, but for some reason confuses people. If you're lucky, you'll run into something like this. We still have to get the t out of the exponent, so let's take the natural log of both sides. When we do that, natural logs and e's cancel out, and I get t equals the natural log of 984, and that is the exact answer. If I want the approximate answer, I just plug that into my calculator, and write down the answer. Now let's try a slightly more complicated one. Alright, I look at this, and again, I try and find a similar base at the beginning to see if it'll solve in the easier fashion, and it won't. So what I'm going to have to do is take the natural log of both sides, and I'm going to use the rules of logarithms to get the variables out of the exponent. So I can bring the x down, and I can bring the x plus 2 down, and when I do that, I have to make sure to remember to keep it in parentheses, because I'm going to have to distribute this natural log of 3 over both these terms. So let's leave this left-hand side alone for right now, and distribute the natural log of 3 over the x. and over the 2. And now I have terms with x's in them, terms without x's in them. So what I'm going to do is get everything with an x in it over on the left-hand side and leave everything else over on the right. So I'm just going to bring this term over to this side. And when I do that, I'm going to change its sign. Like so. And if you remember back, I forget exactly what section it's in, I said there was a trick you'd be using quite a bit in logarithms. Well, here it is. I have 2 terms with x's in them, and I need to isolate the x. So I'm going to divide the x out of each of these terms, and that's going to leave me with natural log 6 minus natural log 3 in the parentheses equals 2 times natural log of 3. Now I have an x. The coefficient on the x, even though it looks rather complicated, it's still the coefficient on the x, equals some number. So all I have to do is divide both sides by the coefficient on the x. They'll cancel. And we have our exact answer. Never ever try and cancel these two because of that minus sign here. We never cancel across minus signs. So just leave it like this. This is your exact answer. And if we wanted the approximate answer, we would just plug that into the calculator and get our approximate answer. And we're done. Now we are going to move on to logarithms. And logarithmic equations fall into 2 main forms. On the first form, you'll end up with a logarithm on one side equaling some number on the other. When you fall into this form, always rewrite the equation in exponential form and then solve. And in this case, fairly self-evident, x is just 25. So let's try something slightly harder. Okay, here it's in the form that I said we'd convert to exponential. We just have something a little more complicated looking in here, but same basic idea. So 5x minus 9 equals 5 squared, or 5x minus 9 equals 25. So let's bring this term over. And when I cross over the equal sign, I change the sign. Divide by the coefficient. And I get x equals 34 over 5. Now, unlike exponential equations, logarithmic equations have a restricted domain. Remember, I can't have a negative in here. So what we're going to do is we're just going to look at 5x minus 9 and ask ourselves, if I plug 34 over 5 in here, am I going to get something that is less than 0 or equal to 0? Because I cannot have a 0 in there either. So all you have to do is plug 34 over 5 in here. If you get a positive answer out, it's good. If you, by any chance, happen to get a negative answer or a 0, you'd have to throw that particular answer out. But in this case, it's good. That's positive when I plug 34 over 5 in there. So 34 over 5 is my answer. The second type looks kind of like this. And what happens here is I have logarithms everywhere. I'm not going to be able to get a number off on one side. And the nice thing about this is that logarithms are one-to-one, just like exponential equations are. So if I get a log base 5 over here and a log base 5 over here, I'm able to throw out the logarithms and just work with what's after them. So all I have to worry about is combining these two. And I can do that now. Like that. Remember, minus means it goes on the bottom. Now I have a log base 5 equaling a log base 5, so I can, for all intents and purposes, ignore the log base 5 and just work with that. Now, we know that we have to get rid of this x plus 6. So we'll multiply both sides by x plus 6. On the left-hand side, they'll cancel out. And on the right-hand side, I'll just have to multiply them out. And it looks like I have a quadratic equation because of that square there. And to solve quadratics, what you do is get everything over to one side and then either factor or apply the quadratic formula. So I'm going to move everything over to the right-hand side instead of the left, simply because I don't want a negative in front of that x squared. So I'll move this x over and this 14 over. And then I'll simplify. Alright, now I really don't like working with these over on the right hand side. You can if you want to. It doesn't make any difference. But I just usually feel happier with it on the left. Again, they're exactly the same thing. It won't matter which way you do it. But I'm just going to switch it over to this side. And now, fortunately for us, this factors nicely. And I get x plus 7 times x minus 2 equals 0, which gives me a solution set of -7 and +2. Now, what I have to do is go back to each one of these individually, the x plus 14, the x plus 6, and the x, and see if either of these will make any of them negative. Well, this one's okay. But if I plug the -7 in for either of these, I'm going to get a negative log. And I can't have that. So I have to throw out that -7. The 2, let's see, it's positive here, it's positive here, and it's positive here. So 2 is good. So 2 is going to be my answer. Now let's try one more of these. Okay, but this time I have a plus. Same basic setup, except here I have a plus, so I'm going to multiply these two together. And I have another problem with that 2 out in front. I can't really start doing this with that 2 there. So let's get rid of that to start. And I can get rid of it by just turning it into an exponent. Now I'm going to combine these two together by multiplying. And now that I have a natural log equals a natural log, I can basically ignore the natural logs and just work with what's after them. So let me multiply these two together. That gives me x squared minus 4x plus 10x minus 40 equals x squared. And it might look like I have a quadratic, but in actuality, this x squared and this x squared, when I try and bring everything over to one side, is going to cancel. So let's just bring everything with an x over to the left-hand side, everything else over to the right. So the x squared's there. I'll bring this one over. I'll leave this one here, and this one, And I'll bring the 40 over to the other side. And again, anytime I cross the equal sign, I have to change the sign. Let's see, these x squareds will cancel out. And I'm left with 6x equals 40. So divide both sides by the coefficient. And I get x equals 40 over 6, which is the same as 20 over 3. Alright, so if I look at 20 over 3 in here, that's positive. If I look at 20 over 3 in here, well, let's see. All it has to be is greater than 4. And I know 12 over 3 is 4, so I know this is greater than 4, so I know that's going to be positive. I really don't care what the number is, just as long as it's positive. And I know 20 over 3 is going to be positive in here. So 20 over 3 is a good answer, and we're done with this problem.